Electrochemical cells. So let's exemplify these. If we look at a very early on battery, the first ever battery, okay, so let's say this thing here is copper. Okay, this metal. And then just beside it, we have another metal labeled as zinc. Now, in between these two things, we have some sort of barrier. Okay, and this barrier could be, paper with salt water or glass wool or cotton or something. Okay, we have some sort of barrier that acts as a medium, okay, between these two metals. And this very, very first battery, okay, this very first battery down here was able to transfer electricity. Okay, so electrons from this zinc over here went in towards the copper. Okay, so what the heck is going on? Okay, so in this very first battery, there was conversion of chemical energy. And obviously we know that these are chemicals, right? Obviously zinc is an element, copper is an element, right? So these are elements on the periodic table, right? So there was conversion of chemical energy. Okay, so this is just short for chemical. Okay, so there was conversion of this chemical energy to electric energy, okay, or electricity. Okay, and you should already know that electricity, or electric energy, is just these flow of electrons, right? So electrons here, I'll just write it here on the side. Electricity is just the flow of electrons. Okay, in physics you should have already learned this is just current, right? Represented as I. Now if we take a look at an in-depth analysis of how this electricity, right, these flow of electrons occurred, it's because of spontaneous redox reaction. Okay, this is the whole series that we're doing about electrochemistry. And the very ever first cell, right, known as the galvanic cell, defined it this way. Okay, it used redox, right, these reduction and oxidation principles. Okay, so we use the redox reaction. Look at this, obviously stands for reactions. Okay, so we use these redox reactions to convert this chemical energy into this electric energy. Okay, and again, this all needs to be spontaneous. Okay, if you have no idea what spontaneous means, okay, please look at the video link in the description where we talk about an in-depth explanation about spontaneity. Now what I have for you here is that galvanic cell that we just mentioned briefly about, okay? And it's a specific type of galvanic cell known as the daniell cell. Okay, so let's see how this works in a practical sense. Let's say we have that zinc again. Okay, so let's say this area right over there. Okay, so whatever is being dipped into this little solution down there, let's say this thing is zinc. All right, so I'll just put Zn. And this thing over here that is dipped into this aqueous solution, okay, this thing is known as copper. All right, and again, both of these are in solid form, as you can see by this stick. All right, so this is zinc as a solid form, and this is copper as solid. Now, what did we say occurred with that bridge that I talked about on the top left corner, okay, moments ago? It was the zinc that was giving away the electrons. Okay, the electrons, the electricity was coming out of the zinc and it was going into the copper. So you should know zinc has a charge of 2+. So 2 electrons went away from the zinc end and went in towards the copper. So let's have it going upwards here. 2 electrons going through this voltmeter that is attached in between the zinc wire and the copper wire, and those 2 electrons are going to eventually flow in toward the copper electrode. So at this point, I want to make sure that I create some partial half reactions to make sure that we don't get lost at any point in throughout this example and illustration. Okay, so let's have, a Zn maybe on this side and a Zn maybe on that side, and let's have a yield symbol in between. Like, we got to figure out which one remains as a solid or which one becomes an ion. Okay, so we're just going to be putting this roughly over here, and same thing for our Cu. Okay, we're going to have Cu maybe on one side and Cu on the other side, and we got to figure out where we put the electrons and where we turn one into a cation. Okay, so again, 2 electrons came out, right? So that means 2 electrons was released. So if it's released, it's obviously got to be on the right side of the yield sign. Okay, it can't be on the left side. That doesn't make sense. So the 2 electrons needs to be on the right side. Okay, so let's put that over here. So it got released, okay? It got produced or released, okay? Same thing in this context. So what does this mean? Well, it's impossible for this side to have a charge or oxidation number of 0, whereas this one over here, the overall charge is a 2-, okay, because it's 2 electrons. So how do we fix this? We obviously know that this here now becomes a 2+, okay, so this 2+ and the 2- here, they're going to cancel out for a net 0, which is exactly what we want, okay, for it to neutralize. And of course, where these 2 electrons are going to go on this side, obviously the left side, okay, because it got received into this area where the reactant are. Let's have 2 electrons over there, okay, so that would mean, of course, in order to balance it out properly for the charges, okay, if this is -2, this has to be a positive, so we're putting a Cu2+ over there, okay, and of course, these ions are going to be in aqueous state. Okay, this one here is going to be an aqueous state, and we've already stated that our Zn at the very beginning that is giving away these electrons is in a solid state, right? Okay, so we can just put that S down there as well, okay, and then this Cu over here, it is taking in those electrons. It's going to still remain solid, okay, that's not going to change, so we'll just be putting an S down there as well. Now, it's important to note that we need to have some sort of solution in both of these test tubes where a precipitate cannot form. Okay, so it needs to be very clear that whatever is in here and whatever is in here needs to always produce a product that is always going to be soluble, okay, rather than insoluble. We don't want any precipitates to form, obviously. So in this particular example, okay, we can use sulfate, okay, because it works out just fine. So if I just state here that this here is sulfate, and let's say this one is zinc sulfate over here. Of course, the 2 goes down here, and then the 2- goes down over there as well. Okay, so hence why we just have ZnSO4 there. And this one over here, in this solution, we'll have CuSO4, okay? Again, it doesn't always just have to be a sulfate, okay? It can be a nitrate, okay? It doesn't really matter, okay? It can be any type of anion, okay? As long as, like I said, the precipitates do not form, okay? So how do we check to make sure that doesn't become a problem? Well, you got to check this little S over here. This S here represents the salt bridge. Now, what is this salt bridge for? So the salt bridge, it's to allow ions to pass without, because of this represents without, solution, this stands for solutions, coming in. Now let's say the salt bridge in this case is KCl, okay? So potassium chloride. If that's the case, we are absolutely fine to use sulfate as our anion, because let's say reaction occurs where this K and this SO4 through double displacement reaction pairs up, okay, so the K and then the SO4, okay, so that'll be K2SO4. If you have that forming, is this soluble or is it insoluble? It's very soluble, so there's no worry about it forming a precipitate, of it being. Same thing if the Zn pairs up with the chlorine over there, you get zinc chloride. Okay, again, this one will be aqueous as well. Okay, just like the K2SO4. Again, this will remain soluble, so there's no worry. And same thing for this one and this one as well, right? So if we had Cu and Cl together, CuCl2, okay, again, this one would be aqueous as well. And what's going to happen is it going to be soluble or insoluble? It would absolutely be soluble. There is no need to worry about any precipitate. So this is why when we have a salt bridge as this, okay, you got to make sure what is our solution that is at the bottom of these test tubes, okay? Are we going to make sure that there's not going to be any precipitate that's going to form as a result of it? Now I want to make this even a little bit more clear, okay? So this Zn and NSO4, obviously it's going to dissociate because it's going to be mixed with water, right? So they're going to break apart, and this is going to break apart into its cation, and this is going to break apart into its anion, right? Same thing for this one over here. So I'm just going to erase these and have them broken up. Let's focus on this side over here. So we established that 2 electrons went onto this copper, right? So if the 2 electrons have now settled onto that copper, so let's zero in on over here, okay? So we established that the 2 electrons jumped into there, okay, on top in order to create more and more Cu, right? The Cus, right, that we see here, okay? It's going to build on top of that. But what is represented in our half reaction? The Cu2 plus, it seems to be on the same side as the 2 electrons. Okay, these are both reactants. Okay, so if 2 electrons are jumping onto this electrode here of Cus, guess what? The Cu2 plus also needs to be jumping onto this electrode as well, because like I said, they're both reactants. Well, then where the heck does this Cu2 plus come from? It's what I just explained down here, okay? This aqueous solution that was added at the very beginning of this whole reaction, right? The ZnSO4, the Cu2 plus, okay? The CuSO4 here, this Cu2 plus that is floating in the solution, as the 2 electrons come in, they're gonna also jump towards that electrode, okay, onto the Cus, okay? That's why we're going to get this nice little half reaction here. Similarly, if we zero in on this side, if the 2 electrons are leaving, okay, so then what's going to happen, okay? Again, 2 electrons are leaving this electrode, right? They're going this way, okay, as indicated over here. That means the Zn2 plus over here needs to leave as well, okay, because it's also being yielded, it's being produced, okay, it's on the product side. So where is the Zn2 plus? Well, it can't really, you know, float upwards or anywhere, okay, it's just gonna fall out. So then what is surrounding this electrode, right? Obviously it's this liquid aqueous solution here. So of course this Zn, okay, this electrode over here is going to release, okay, the Zn2 plus into the solution. Okay, you can't really see it here, so I'm just going to release it over this way. Okay, so now you have that Zn2 plus, okay, right over there. I want to do it in green here so you can see it more clearly. Okay, so the Zn2 plus is in the solution, whereas on this side, I'm just going to highlight it one more time for you, right? Whereas on this side, the Cu2 plus is now joining on top into the actual electrode. Now, however, we are not done, okay? Even though the Zn2 plus over here, okay, has gone into the solution, this means that it is way more positive now, okay? This solution over here is very positive because we have Zn2 pluses joining into the solution, and we actually lost 2 electrons leaving, okay, as exemplified here. So we need more negatives, okay? We need more negative charges to come back into this solution. So what's going to happen? The KCl over here, our salt bridge, okay? The Cl minus, the ion, okay, the anion version, okay, within this compound is going to dissociate, and it's going to fill the void by going in towards that solution, okay? So the Cl minus here goes in downwards, goes towards the left, and then jumps down into the solution. So now we have Cl1 minus in here to make it a little bit more negative to get that neutrality. Similarly, this K plus, okay, that K within this KCl does something similar, goes down, okay, on a separate pathway. It goes towards the right, goes down, and now we have K plus in the actual solution to make it slightly more positive. Since we lost so many of the positives from this Cu2 plus, that left that solution and latched onto the electrode. All right, let's look at this question here. Galvanic cell, this time involving zinc, okay, same thing, but magnesium this time, okay? Which electrode will be the anode and which one will be the cathode? In order to solve this, you need a reference chart like this. Okay, this here is called the reduction potential chart, okay? And as you can see here on the left side of these half reactions and these values, we can pinpoint what our metals are and where they stand on this chart. The higher up you go on this chart, okay, it increases strength as an oxidizing agent, okay, whereas as you go downwards on this chart, it increases strength as a reducing agent. So let's start with one by one, okay, so let's start with zinc over here. Where is zinc on our chart over here? As we can see, it's right there, okay, near the middle. So the zinc here is higher than the magnesium. What does that mean? Okay, that means this Zn, okay, it is stronger as an oxidizing agent, okay? Remember, if it is stronger as an oxidizing agent, that means it is acting as that oxidizing agent, okay? It is a stronger oxidizing agent. What do oxidizing agents do? They help the other partner oxidize, okay? So this, because it's a stronger oxidizing agent, it helps oxidize its partner, and its partner in this case that we're dealing with in this question is Mg. So this Mg here is going to get oxidized. All right, so I'm just going to put here the Mg is going to get oxidized. And you should always know that anode represents the end that gets oxidized. Okay, so I'll just put anode here on the side. Okay, so to answer this question for the first half of this, okay, which electrode will be the anode? The Mg is going to be the anode. So of course, vice versa then, right? The Zn is going to be reduced. Okay, and we should already know that cathodes are the electrodes that get reduced. Okay, so I'll just put cathode over here. Okay, so the second half of this question, to answer it, okay, the Zn is going to be the cathode. Number 2, it is asking where is the oxidation, okay, and the reduction occurring. Okay, so that's kind of already answered in the previous question, right? So like I said, the anode is the end, right, the electrode end that gets oxidized, whereas the cathode is the electrode end that gets reduced. So this kind of already answers the question. All right, so let's have a look at this question here. And it's asking us to indicate the direction of electron flow through the use of a diagram. Okay, so in the previous example, we had Zn over here, right? And we had, I think, copper over here. Do I keep it similar? Okay, do I keep the Zn over here? And do I keep my Mg as my new side on this side over here on the right side? What do you think? Take a second to think about this. It really doesn't matter, okay? It could be going this way as long as you indicate that it is being oxidized, okay? It is losing electrons, okay? Or you could just put the Mg here on the left side and the Zn here on the right side, okay? Because we've already dealt with this direction, okay, going to the right side as the flow of electrons. So if you want to keep that same route, that same pattern, okay, if you like it better that way, then you should put the Mg on the left side. Okay, so the Mg here is a solid. Obviously it's a solid metal, okay, same as zinc, okay, like most metals are. Now we got to figure out our half reactions. Okay, so let's say Mg, it is yielding another Mg over here, and let's say we have a Zn here yielding a Zn. Okay, let's figure out our transfer of electrons. Again, Mg has a charge of 2 plus, so those 2 electrons, okay, are going to leave, go into the voltmeter and then go through this end over here and go onto this electrode, right, the Zn. If that is the case, we got to be putting our 2 electrons, okay, on the product side because it is yielding it, okay, it is releasing those electrons. That means this Mg here becomes Mg2 plus. Now again, this one here was a solid, right? I forgot to keep that there, okay, right over there. So then on this side over here, the 2 electrons are coming in, so we got to be putting it on the left side of the equation, obviously, okay, and then that means if this is a -2, this has to be a +2, so we're putting a +2 over there, okay, and of course this is aqueous, right? So let's put aqueous over there. This is also going to be aqueous now, and the Zn here, the one that is getting the electrons added on, okay, is going to be the solid one, okay, so I'm just going to put solid over here. Now what is happening in this solution there and what's happening in this solution there? Well, we first got to make sure we have a salt bridge that we reference it with, right? So what is our salt bridge and what are our solutions? What do they have to be so that there is no precipitate that forms? Let's use KCl again, okay, like we did in the previous example, okay? So then what would this solution be? What would this solution be, okay? Again, there could be multiple answers for this, okay? Maybe pause video, try to think about it. What do you think would work as a solution in these 2 little test tubes? So hopefully you've been able to figure out and use a compound that works, okay, where it doesn't produce a precipitate, okay. Nitrates are honestly the easiest ones, okay, because pretty much any cation with a nitrate will be soluble. So I'm just going to be putting nitrates in here, okay. So because nitrates are the easiest, I'll just put that over here. Again, it has to be paired up with an Mg, right? So again, this would be an Mg2 plus, right? So we're going to be putting an Mg2 down here on the bottom. You can't really see it, so I'm just going to make it green, okay? So on the bottom there, and then the Zn, same thing, we'll have an NO3, and then 2 on the bottom over there, okay? And again, this whole thing and this whole thing is aqueous. And of course that's going to dissociate them, that's going to break them apart floating within the water, okay. So we can actually just do that right now, okay, break them up so it's easier to see. So you'll have Mg2 pluses floating around as well as NO3 minuses floating around as well, okay. And then on this side here we'll have Zn2 pluses floating around and NO3 minuses also floating around, okay. So if you were to pair this K with this NO3, okay, it's going to be soluble. If you put this Zn and Cl together, okay, they're going to be soluble. If you put this Mg with this Cl, okay, that's going to be soluble as well. And if you put this K with this NO3, that's going to be soluble too. So we don't have to worry about any precipitates forming now, okay. So let's finish this off. The 2 electrons are leaving, okay, it's leaving this area, which means it's going to be highly positive in this place over here. So how do we make it a little bit more negative so we can neutralize it? Okay, this Cl minus here, this from the salt bridge, is going to be negatively charged as an anion. So what's it's going to do? This Cl minus is going to go down and go into this solution here. And similarly, this K plus is going to go down from the salt bridge into this area and add some positivity, okay, in that solution. Because like we said before, if there are 2 electrons on this side, on the reactant side, guess what? There's also Zn2 pluses on that reactant side as well, okay? So where is that Zn2 plus, okay? This Zn2 plus went into that electrode, right? So the positives are no longer in that solution. It's now on the Zn electrode, leaving this solution to negative, okay? So that's why I added that K plus in there to help neutrality. Right, number 4, it's saying indicate the direction of the ionic movement in the cell. I think we kind of already did a lot of them, really. We've just talked about here on this side that the Zn2 plus, right, was like the two electrons going onto the ZnS electrode, right? It's going onto this electrode over there, right? So the electrons going over here, the Zn2 plus going on into there, okay? How about on this side over here, the two electrons are leaving, okay? What else has to be leaving then, right? There's two electrons here left. This Mg2 plus also needs to leave, okay? So where did this Mg2 plus come from? It came from this Mgs, okay? That's this electrode over here, this Mgs. So it went from here and it left, okay? Went to this side. So where is that Mg2 plus now? Okay, well, it just jumped into there, right? Into the aqueous solution. So I'll just put it in green over here. The Mg2 plus now is there. Okay, hence the reason why we brought in this Cl minus in the first place to help the neutrality from the salt. Alright, let's write a balanced ionic equation that represents this reaction. Okay, so we have this one, we have this one. So we're just going to put these two half reactions together. Let's stack them up on top of each other. Let's add this one. So what can we cancel out? Okay, two electrons cancels out with that, and there's nothing else we can cancel out, so we are done. Okay, so let's put the reactants together and then let's put the products together. So we have Mg S plus Zn 2 plus AQ yields our Mg 2 plus plus our ZnS. That's the answer. And don't forget the aqueous there. Alright, so this is the green question of the day. It's separated into 5 different parts. That's great practice for you. Please pause the video, try this on your own, and I'll be giving you the answer shortly. This is the answer to the first question, and the second question. I will slowly scroll down for the third.